All right, welcome back to our fourth lesson on electrochemical kinetics, and we're just going to discuss a few other concepts in kinetics. So first off, we want to talk about inner sphere and outer sphere reactions. Inner sphere reactions are reactions where your analyte and the surface of your electrode interact directly. And here's a diagram or two of what it might look like at the surface of our electrode. And then outer sphere reactions, that's when our analyte and our electrode are separated by at least one solvent layer. And what that means is that we don't have to deal with complications like adsorption and desorption, and so that makes the math a little bit easier. But it also means that how the electrons are getting to this analyte is through electron tunneling. And so they're tunneling through an energy barrier from our electrode into our analyte or vice versa. The next thing that I want to talk about is Marcus theory. This is a good thing to be aware of. It's very useful. It's predicted a few things in electrochemistry that are powerful. And so I just want you to have a basic understanding of it. And the basic understanding is that we're upgrading our free energy surfaces from being linear to being quadratic. And so, our expressions are a little bit more complicated, and we're going to have these Q terms, and these are related to the reaction coordinate. So QOX, that's kind of the equilibrium reaction coordinate for the oxidated species. And then same for Q red. And then Q is, where we are on this combined energy surface. So once again, we have a transition state, and we have changes in Gibbs free energy for the forward and the backward reaction. It's very similar to what we had going before, but just with quadratic expressions. So we're going to define this lambda term. We're going to write out a little bit more complicated expressions for the transitional Gibbs free energy. Here we have these delta W terms. That's the work involved in rearranging our solution, getting our analytes where they need to be. And then we can define the transfer coefficient from Marcus theory. And you'll see that what we end up with is the transfer coefficient is equal to 1/2 plus some terms that modify it slightly, which is a really satisfying conclusion to make, because a transfer coefficient of 1/2 is what is standard. That's the most common transfer coefficient in electrochemical studies. Next, I want to talk about open circuit potential. So we can define it simply with the Nernst equation when there's a single redox couple. Here, this would be for an ion and its metal as the electrode. But what if there are multiple redox couples in our system? Well, then how the open circuit potential is defined is when the currents all bounce out to zero. So for our forward and our for all of our different species J, their currents need to balance out at zero. And we could calculate this using the Butler-Volmer equation, for example. Next, I want to talk about the multi-step multi-electron transfer reactions. So let's say we have a rate-determining step. This is an outer sphere reaction, and the first step is irreversible. So our rate is going to be determined by the rate-determining step. And we write out our two reactions here. Here we have the net reaction that's occurring, and we write out our current here with the rate determining step, equilibrium, rate constant. We have our transfer coefficient for the rate determining step. And then you'll notice here we're missing the backwards reaction to including the concentration of the redox species because of the irreversible first step. Here, this is another example. So we have a rate determining step and a quasi-reversible reaction. And here, this middle reaction, that's the one that's our rate determining step. So we have a pre-reaction and a post-reaction, but this rate determining step, this is the slowest reaction by far. We can write out the net reaction. We can write out our current expression here with our rate constant, or with our rate expression. And then we toss in our variables for our pre-reaction, for the rate determining step reaction, for the post-reaction, the rate determining step, and so forth. So those are just little tastes of what goes on in some more specific applications of kinetics. And I just want you to answer these questions before we finish up the video. So go ahead and pause the video now, and in a few seconds I'll give the answers. Okay, so how does Marcus theory upgrade from typical free energy surface diagrams? And what it does is it treats the curves as a quadratic expression instead of as a straight line expression. And the next is, how could you tell if something is an inner sphere or an outer sphere reaction? Well, an inner sphere reaction, it occurs at the electrode. And so, as you might guess, if you change the electrode substrate, how your reaction proceeds will actually change. Whereas an outer sphere reaction will be largely independent of what your electrode is made of. Okay, well, thanks. We hope you'll join us for our final lesson as we talk about mass transfer. Thanks.